Is it visible?
Yes, sir.
Okay. So first, I am thankful to Professor Singh for giving me this opportunity to talk to you about some facilities which I have titled as opportunities in the field of astrophysics in India. And I am really honored to be the, providing you first lecture. This is a very interesting program which I just read, and I wish all the success for this program in its future. Let me briefly come back to my topic. And this is why I chose this, because this has been, as you just heard from the introduction, right from, I did my M.Sc from Gorakhpur. My specialization was astrophysics. So I knew, I can say that I have over 5 decades of experience working in the area of different aspects of astrophysics. And that's what I thought it will be nice to share, as some of you are looking forward towards what are the opportunities and so on. Is my voice is correct? Okay, or something is needed?
Sir, it is fine.
Okay, fine. Then I'm just continuing. So first, what I'm going to tell you, astronomy, astrophysics, or sometimes we call, celestial bodies, physical sciences of celestial bodies. That's what I will introduce. And then I will mention about space and ground-based observational facilities, because these celestial bodies, they are very far and they are located at such a large distance that we only receive some sort of what we call now multi-messenger, that is electromagnetic radiation, neutrino, or even today we can say gravitational waves. Those type of information we receive, and for that we have to have what we call observational facilities. So that's what I will try to, just mention about them. And then, as you just heard, Devasthal Observatory, which is hosting Asia's largest size 4-meter class optical telescope. In fact, this I spent more than 15-16 years of my academic career in this project. So I will definitely would like to talk about it. And then I would like to mention about multi-messenger mega initiatives, which has been taken by Indian government, and I will name them, provide you some information, and also in a sense I will tell you about the present status of 30-meter, that's the very large telescope project where India is participating, and also India is thinking to build a 10-meter ground-based optical near infrared telescope, which will be located in Trans-Himalaya region, somewhere in close to Hanle region. So this is my background of the talk. Let me just introduce then. As I told you, although historically we call it astrophysics, but it's a science of celestial bodies. And during last couple of decades, it's not only physics, but astrochemistry, astrobiology, those things have also come into picture. So if we, study those aspects, that's what we call astrophysics broadly. And it means, we are trying to understand physical, biological, chemical processes in celestial bodies. And what are those celestial bodies? They could be star, they could be planetary system, it could be interstellar matter, galaxy, etc. And why we study them, and in fact, I am happy to share with you that this is a very, very crucial, part of physics. Why? Because these celestial bodies, they provide us giant natural laboratories, which we are not able to produce on Earth. For example, if we take center of a star, like our sun, they have very high temperature at the center, which ranges from 10 lakh to few thousands lakh half kilometer, and under very high pressure, nuclear reactions take place, which is the source of energy. And those type of things at such a vast scale, we are not able to produce on Earth. If we talk about mass, then just like in our CGS system, we generally talk of kilogram and so on. Here, solar mass is the unit which we quite often use, and one solar mass is 2 into 10 power 33 gram. That is the unit of mass which we are talking about. So huge mass we are talking. If we talk about stars, they have a range of 0.1 solar mass to roughly 100-150 solar mass, depending upon which model we are using. If we talk about galaxies, then as you can see, 10 power 12 to 10 power 13 times solar mass, that is the mass range. If we talk about density, then we have extremes of density. For example, if we have neutron star, even one spoon of that neutron star material we cannot lift. It's very heavy. Its density is 10 to the power 12 gram per cc. Contrary to that, if you see, there is a space between stars and galaxies where it's a pure, fully vacuum, you can see. The density is 10 to the power minus 24 gram per cc. So all these physical conditions, they really provide a laboratory which we don't have on our Earth. And in fact, if you look into the history of physics, there are many theoretical ideas like Einstein's relativity and many more nuclear physics related things. They were first tested in these celestial bodies. Only problem or major problem is that they are located at a very far distance. And distance of these objects, they are measured generally in light year. And 1 light year means, speed of the light is, it's 3 lakh per kilometer. Sorry, 3 lakh per second. 3 lakh kilometer per second, that is the speed of light. So if you convert that into seconds, minute and days, and then year, and if you multiply, then 1 light year is equal to 9.46 into 10 power 12 meter. So generally the distances we measure in light year, and the nearest star next to sun is about 4 light year away. If we talk about the galaxies, then they are, several mega light years away. So the main question is how to observe them. So this diagram basically shows that these are the celestial bodies, and only information which are emitted from them, they are in the form of messenger, what we call multi-wavelength messenger. They have electromagnetic radiation, and most of you know that in physics, electromagnetic radiation means it goes from high energy to very low energy. It means gamma ray, then you have X-ray, ultraviolet, and if you go to the lower energy, it goes to the radio range. Then we have neutrinos, gravitational waves, and cosmic rays, which are emitted. And in fact, more detail, it's published in this Journal of Astronomy and Astrophysics. So these, objects are located very far. So the signal which reaches, it travels first through the interstellar matter, and then it enters into the Earth atmosphere. And that is where, as you know, if you have a wave which is entering into any medium, then attenuation and degradation of its phase, because waves are characterized by amplitude and phase. So when amplitude is get affected, it means we have what we call attenuation. When phase is affected, then the image what we get, it's not very sharp, but we get blurred image. And that's what happened is the limitation while we observe from Earth. I will talk more about it later on. But basically, if you take a simple glass full of water, throw light from one side and to the other side. If the water is steady in the glass or whatever container you have, your only attenuation will take place. But phase, there will be some sort of difference, but it will be not blurred. But if you vibrate the medium through which light is passing, you will get blurred image. It means the phase is also getting affected. And these are the things which affect our astronomical observation, and we have to correct them while we are trying to learn about these celestial objects. And this diagram basically tells us that Earth, we are here and we are talking with each other basically because of the fact that these high energy photons, they are blocked by our Earth atmosphere. So UV radiation is not transmitted. Only a very narrow window of optical, some part of near IR and radio. So these are the only part of the electromagnetic spectrum which is able to reach, and that's what you can see below. That's why we have radio telescopes which observe at the radio wavelength. We have optical telescopes, near IR telescopes, which are used to take observation at optical and near IR wavelengths. But these which are opaque, where we cannot observe from ground, only space era is there. And fortunately to us, the first satellite was launched in 1957. Since then, development in technology in the space and other areas like communication, all these things have helped. So for gamma ray, X-ray and ultraviolet, all these observations, we have space probes. Even you must have heard recently that NASA has launched a near IR telescope, and that's giving a beautiful images and information about it. For that, space probes are there. So that's why we say ground-based and space-based observation. And I will basically, now this slide is trying to emphasize why we need these type of observations. As I have mentioned that these celestial objects, they are located very far. So how to know about it? So the best way, as you do, spectroscopic in laboratory, and from spectra of the, sources, you find out what are their characteristics. The same thing is done for these celestial bodies. If we have wavelength, energy spectrum, then they tells us what is the source of energy generation. For example, if we take a star, and if it is a thermal, then it can be approximated as a black body radiation. But if we have synchrotron radiation in many celestial bodies, the source of radiation is not thermal, but it is synchrotron, then the energy distributions are different. So it means we need multi-wavelength observations, means right from ultraviolet to radio, to study their behavior and to know about them. Now, as I mentioned you, my career has been basically in optical astronomy. So my remaining part of the talk will be basically towards optical astronomy, and in that, why optical telescopes are very important. In fact, आपके विभाग में भी, एस्ट्रोफिजिक्स में भी, when we were studying, 6 इंच की दूरबीन थी. अब मुझे जहां तक जानकारी है, इससे बड़ी दूरबीन है आपके पास, आप उसको देख सकते हैं. और टेलीस्कोप, always we call name of the telescope as a diameter. Whatever is the diameter of primary mirror, that telescope is named by that. So जैसे कहते हैं 1 meter telescope, it means its optical diameter is 1 meter. जैसे मैं आपसे बता रहा था कि आपके विभाग में हम लोग जब प्रैक्टिकल करते थे तो उन दिनों 6 इंच की टेलीस्कोप थी. इसका मतलब उसका डायमीटर 6 इंच का है. So ये काफी, it provides very valuable information for astrophysical studies. And in fact, if you look into the history, it is as old as human civilization, because our eye, God gifted, it's a natural telescope. Only limitation is it has very small pupil size, which is about 6 to 7 millimeter. So that acts like a telescope, and our, retina acts like a detector, and mind acts like an analyzer. So that's why, as soon as a human being, he started looking around, not only they saw forest and other things, but they also saw stars and that type of objects, and then they were curious to know about it. But a major change in the, our understanding came when first time Galileo, in 1609, used a very small size telescope, and many observations, then they deciphers the secrets of the universe which we were not able to see. So recent developments in computer electronics in another area, they have significantly contributed to our understanding. And yeah, I will try to touch upon them, and all these things will clearly also show you that this field has enormous opportunities, not only for physicists, chemists, or biologists, even for engineers, because the type of, observing facilities you build, they need always cutting edge of the technology. And I will try to touch upon them only towards the end of this, where 30-meter telescope, as I mentioned to you, India is, having partnership in it. And some of the, I will say, crucial component of the telescope, they are being built in India. So this slide basically tells you why, we need large size of telescope. It's because it's like rain gauge. If you have a larger bucket, you collect more and more water. So that's what we call light gathering power, and it is directly proportional to the area of our, primary mirror, and that's what is reflected here. That light gathering power is equal to D is the diameter of the telescope, and S is our pupil diameter. And if we say for 4-meter size telescope, then light gathering power is equal to 25 into 10 power 4 into T. And T is very important. T is because we always use detector, we use, some sort of collimating optics. So all these things, they produce some losses, and that's what called losses due to optics and detector. And D is the diameter of the telescope, and S is the diameter of pupillae. So this you can see easily that why we need larger and larger telescope, because we want to see fainter and fainter objects, and we want to resolve them with better angular resolution. And these are the two essential things which are required, and that's why we want to build larger telescope. And this is very important. You must have heard that most of these observatories, they are located at an altitude more than 2 kilometers. For example, in Gorakhpur, you must have noticed that you have, fog and many weather affected things, and our aerosol contents are very large. But if you go above 2 kilometers, that's where we say atmospheric boundary layer, they changes, and the aerosol content reduces. And that was one of the reasons. If you see the history of even Aries, it started in Varanasi, and finally, because of these, atmospheric conditions, it moved to Nainital, and to its present location to Devasthal for other, characteristics. So site characterizations are very important, and also they are very useful to finally decide what type of telescope we need for our observations. This slide really tells us, the earlier slide tells us, they were informing us about the light gathering power. This tells us about the angular resolution. As long as human eye was there, that is till the Galileo used its first telescope, as you can see, it was a quantum jump in the angular resolution. And the other quantum jump came not from the ground-based telescope, but it came when HST, Hubble Space Telescope, was launched. And this region is basically our Earth atmosphere. It blurred the images. And that's what I have tried to mention here. And resolving power in physics, you must have heard, read it, that it's 1.22 lambda by d. So it's a function of wavelength as well as diameter. And if you convert into that unit, you will find what is the value. And for any telescope which is of the order of about 15 centimeter, this resolving power comes about arc second. And Earth atmosphere at most of the places, it produces a blurring effect. And why it is producing blurring effect? Because atmosphere is not static. Earth atmosphere is dynamic. And if we call it static, it is only for some few milliseconds. 20, 30 milliseconds, you can call it as a static. But if you are going for any longer time, then it's no more statics, and that affects, it produces blurring. For the, that astronomer call it as a seeing. So I think for students, I will use the word blurring, which is more appropriate to the phenomena. And best value on the Earth, we can get only 0.3, 0.5. And it is because of this region, as you can see, the diameter increased from this to even 10 meter, but our angular resolution had never improved, and it was always dictated by blurring of the Earth atmosphere. But ground-based telescope, as soon as we go above Earth atmosphere, then blurring effect disappears, and then it is the optics and diffraction limited image we can get it. That's why we are able to have two, I will say quantum jump in our improvement. For example, what we call that Hubble Space Telescope produce images which are having 0.1 arc second, contrary to 1 arc second on the ground based. So we say that Hubble Space Telescope has brought universe 10 times closer to us, because angular resolving power of the telescope is 10 times better than what we generally get at the ground based. This is one of the example of HST. You see, it is a star cluster. Its central region was never resolved by ground-based facilities because we had not very good angular resolution. But when they were resolved, you can see different type of stellar population. Blue stars, which are white dwarf, and very high, I will say, ultraviolet, emission is there. Those type of objects we can study in the nucleus of the things and learn more about such objects. Now I will basically try to inform you that what are the observing facilities which are having diameter optical telescope more than 1 meter in size in India. So, they are in different part of the country. If we start from south, then it is Kabulur. And in fact, Kabulur and Hanle, which are the two extreme in this map, they are both operated by Indian Institute of Astrophysics. And in Kabulur, the largest size we have 2.34 meter Benu Bappu telescope. In fact, for Benu Bappu, we call him as a father of the modern astrophysical studies in India. And he has contributed a lot to the growth of optical astronomy in the country. So this telescope is named after him, and it was installed in 1986. Incidentally, that was the year when I joined IIA as a science faculty. And if you see the other, like we have Japal Rangapur, where we have 1.2 meter, we have Ayuka Pune, Giravali, where we have 2 meter telescope. We have 2.5 meter telescope under installation at PR Mount Tabo and 1.2 meter, which is operating. And this Nainital thing, I will be talking in detail. And we have one, 104 centimeter, which was installed in 1972. And in fact, next month, they are going to celebrate 50th successful operation of this telescope, which has been very useful. At least this was bread and butter for many of us. And what are the important science it has produced, they will produce. And next slide, I will talk about the Devasthal Observatory. So you see, from the earlier presentation, it becomes very clear that if we have atmospheric conditions which are stable, which are not very turbulent, then our observations, astronomical observation, ground-based optical observations can be, it will be very good. And to do that, there are certain characterizations which needs to be carried out. So this has over a decade of site characterization, that is measurements. And that's when, after all these measurements, Devasthal was identified as a potential site. And I am happy to share with you the location which was identified about 15-20 years ago. Because of its physical, geographical topography, it is still giving good result when the telescope operates. And that is a very positive thing. What I mean, it has a topographical structure which is very conducive for a stable Earth atmosphere. Means it is producing least blurring when we observe the celestial objects. And that's where we have established these 3 telescopes. In fact, the 3.6 meter, which is called Devasthal Optical Telescope. It is the modern, and I will say it is the largest in Asia. And this project, it started in 1976. As I mentioned to you that I completed in 1973 and joined UPSO Observatory in 1973. People started talking about this project in 1976. But because of many reasons, which are detailed somewhere else, for example, in the articles which are published, I'm not going to repeat them here. But briefly, I can mention it's the identification of site plus approval from the government, because this project cost about 200 crore total. And optics we cannot build in our country. For example, the primary mirror, which is 3.6 meter, it was built in Russia. And mechanical structures, they were built in Belgium. And this is one telescope where Belgium has, is participating in kind. They have, in cash, not only in kind. They have contributed 2 million euro, which is in today's currency, you will say roughly about 16 to 17 crore rupees, and they are partner. 7% observing time of this telescope is taken by them. Few characteristics I will just mention. This is the primary mirror, which is 3.6 meter, and it's housed in a very compact and modern building. And characteristics of the building is such that it produces least thermal gradient, and that was a modern technology has been used that, so that blurring our atmosphere should not become turbulent in front of the telescope. And total weight of the telescope is about 150 ton. So transportation from Belgium, where it was, assembled first, to Devasthal, it took more than a year. And single component is something like as heavy as 15 ton. So as you can see on the hilly terrain, some of you must have seen, transportation was a big issue, but finally it's in place and it's being used. And I'm happy that Gorakhpur, your department has, making use of this telescope. And in fact, Anand et al. Have published one of the results, which is based on this telescope. Other thing which I am happy to rather note that you have a long-term MOU with ARIES so that your student can use the observing facilities of Nainital Observatory, which I still call Nainital. Of course, it's ARIES, and you can take benefit of it because it's under, after moving to DST, a lot of observational facilities, not only in astrophysics, like in solar physics, as well as in atmospheric physics, they are growing, which you can make use of. This is the Devasthal Observatory. So as I told you, this is 3.6 meter. This was 130 centimeter. It was the first which was installed there in 2010. And this is a 4-meter size liquid mirror telescope. This may be surprising to you that most of the telescopes are, mirrors are made of glass. But what is the purpose of the glass? To reflect the radiation, electromagnetic radiation, and focus it at the, primary focus of it or secondary focus, depending upon the optical system. In this case, instead of glass, a rotating bowel of mercury is used. So once it rotates, then because of rotation, it occupies the shape of parabolic mirror, and surface of it is reused as a reflecting. And in fact, it has started giving images of celestial bodies recently. About 6 months ago, they have taken first image with this telescope. Only disadvantage is that it cannot be moved just like your other telescope. It is just looking at the zenith. So sky passes through it and you observe whatever is celestial object located in that direction, that is at the zenith. But it is very economical in comparison to 200 crore. This has cost about 5 to 6 crore only. So that's the cost you have to pay, that it cannot be used for multi-purpose. It has limited use. And for science and research education, published by Springer Academy, and this is the reference which I have mentioned here. Now I would like to, in the remaining few minutes, tell you that what are the multi-messenger major observational facilities at other wavelength. I have mentioned about optical. You must have heard AstroSat, which is a unique multi-wavelength space observatory. It was launched in 2015. Its lifetime was 5 years. It has completed. It is still operating. And more information is published on the Current Science, Journal of Astrophysics, Astronomy. And these are the details which are given. And you can go through it in detail. I'm just mentioning here, and this has, it's a unique type of observing facility in the sense that simultaneously this observatory was able to observe in ultraviolet, X-ray, as well as optical, and that was the uniqueness. Other space probe, whatever we have, they have better capability, but at only one wavelength, either X-ray or either UV or and either gamma ray or other things. But in this case, that was the beauty. Other thing where one of our colleague, Dr. Durgesh Tripathi, is actively involved. It is a space-based astronomy project, Aditya, and in fact, it's along with Chandrayaan-2, they are progressing well in the laboratory, and more details are given in the Current Science, and these are the volume number and page number. And Professor Durgesh Tripathi is actively contributing to this project. This is an upcoming project. In fact, this will be the future. Based on the success of our AstroSat, ISRO has agreed and given seed money, and this article, which is in press, it's published in JAA, and it's INSIST called. It is 1 meter ultraviolet space telescope. And that's what we expect that during next 10 to 12 years. All these projects, what I'm mentioning, they take very large time because of many reasons, which if you start looking into that, you will realize it. Presently, this I mentioned, it's going on. 30 meter, I will talk a little bit more. These are the other observational facilities which are India is planning, like Neutrino Observatory. More details are given here. LIGO, where IUCA is playing major role, and Department of Atomic Energy is playing major role. And we have also people have started thinking about how to build 10-meter class national large optical IR telescope, and more information you can read in this year, this volume 43 JA and article 32. It's already on website. Other than optical and space telescope, what I mentioned, India is very actively involved at radio wavelength, where they have upgraded GMRT, and more details you can read in this, literature which are listed here. And a square kilometer array, this is another mega project. I mean, this and 30-meter telescopes, they are both, and our LIGO, these are approved, and these are very ambitious project. At gamma ray wavelength also, these are the facilities which are being, I would say, built and being operated. So as you can see, we have multi-messenger facilities, and in fact, more information you can get. These are the application. I can conclude these two slides that all these initiatives take long period, few decades in fact, and need dedicated teamwork, but provide golden opportunity for the growth of modern observational astrophysics. So that is, I will say, it's a takeaway message for our next generation, that there is a lot of potential. Only thing that crowding is there on the ground, but if you move up, there is all, sky is the limit. So if you work hard, sincerely, and all those things, you can take advantage of these opportunities. This couple of slides, I will just show you what is the present status of our 30-meter telescope. In fact, there were 3 mega, telescope projects of diameter 24.5 meter, 30 meter, and 39 meter. All 3 are parallelly progressing. And in the beginning, we decided to participate, in fact, in one of them, and it's a Indian astronomer led by ARIES, IIA, and IUCA. They are taking lead role, but various institutions across the country, they are participating in it. And in October 2014, green signal for this project was given from the cabinet. And you see, these are some of the parts. Much of this participation is in kind. About 70% of the participation is in kind, and we are participating at the 10% cost. And I'm happy to tell you that a good number of them, like segment, we are making 115 to 150, and successfully prototype has been demonstrated. Actuator, they are being made in India. Segment support assembly is being made in India. Edge sensors are made. So these are very crucial component, and they will help us to develop these cutting edge of the technology in our country, and they will be used in building 10-meter class telescope in India. So that's the nutshell. That's our plan, and this is the last slide, which I leave it to you, and in a sense, that's what I spoke. Basically, modern ground-based telescope and space telescope provided us unprecedented angular resolution and has brought the universe 10 times closer to us. Also, with innovative technology like thin and segmented mirror technology and advancement in computer electronics, telescopes have become cheaper than what they were 30 to 40 years ago. And as a result, ground-based optical telescopes as big as 40 meter they are being designed and built. People have already started thinking how to make 100-meter size telescope. And in fact, what people say that this field has enormous potential for discovery due to its vastness, and it could be more than one every day. And some of the things I would like to, in concluding regard, that you might have heard that at high energy, people are trying to create mini, what we see Big Bang laboratory in Europe, where India is also participating. So there are many exciting projects in various branches. I have touched upon only in astrophysics, particularly highlighted optical part. That's all. Thank you. Thank you very much.
Thank you, sir, for your precious time. I'm saying that if any participant have any question, can raise their hand.
Yeah, and I will be happy to take them.
Sir, there is 2 questions in a chat box from one of the participant. Sir, the first question is, sir, let me.
Should I come out of the screen or what to do?
Sir, you can come out of the screen and I'll tell you the question. Hello. Sir, the first question is, sir, is there any link for weather forecast with astrophysics?
Not because weather forecast and astrophysics, these two things are separate, because weather is basically dictated by our Earth atmosphere up to 2 kilometers above the sea level. On the other hand, if you see our celestial bodies, they are located very far. Of course, one thing I must mention, otherwise Durgesh will be very unhappy. You see, the sun, which is the nearest star, there are many type of energies which are emitted, and they affect our Earth atmosphere, including communication. So, but not weather directly so much, but communication and many other things it affects. So that type of effect which I can mention about, in our Earth from the nearest star, sun.
Okay, sir. So second question from the participant is that how these observations of astrophysics useful for industry or business benefits?
Oh yes, it's an excellent question, because that's what all the, as you can see, I said 200 crore, and why it took 30 years, 40 years. Part of the reason is, and that was one of the reasons why the state government said, sir, your projects are nice, but we will be not able to fund you, but we will be happy to transfer you to the government of India. And I'm very happy to attend this question. Yes, let me attend one by one, because it's a very important question. As I told you, you are always trying to use cutting edge technology, and I will give you 2 examples which may, answer your most of the question which you just asked. आप जानते हैं सैटेलाइट 1957 में पहली बार छोड़ा गया, राइट?
ओके सर.
और जबकि जिन सिद्धांतों पर सैटेलाइट छोड़ा गया, करीब 350 इयर्स पहले ही प्लैनेटरी मोशंस के बारे में जाना गया. सो इट टुक more than 300 years to develop technology. तो एस्ट्रोफिजिक्स क्या होता है कि आपको एक फिजिकल कंडीशन, प्योर साइंस की ग्रोथ को ये देता है, एंड अप्लाइड साइंस ऑलवेज फॉलो इट. Best example I can tell you, today all of us, we are using mobile camera. Why we are able to use, and photographic plates are no more used. It's a solid state detector, and it was first time developed for the use of astronomical observations. So as a spin-off, जो सॉलिड स्टेट डिटेक्टर है, आज मेडिसिन में आप देखें, आप हर सभी के पास हर मोबाइल में एक कैमरा है. दिस सॉलिड स्टेट डिटेक्टर इज वन ऑफ द बेस्ट एग्जांपल. और जो मैंने आपको बताया सैटेलाइट स्पेस एरा का जन्म जो हुआ, उससे क्या हुआ आप देखिए, इवन इट कंट्रीब्यूटेड टू द ग्रोथ ऑफ आवर कंट्री, इकोनॉमिक कंट्री। अगर आप आज से 30 साल पहले देखें तो हमारे देश की इकोनॉमी स्ट्रांगली डिपेंडेंट ऑन एग्रीकल्चरल प्रोडक्ट्स मेनली। आज के दिन आप देखें तो एग्रीकल्चर, जैसे आप देखिए गोरखपुर साइड में कितना सूखा है, कंट्री बाकी देश पार्ट में फ्लड है, लेकिन इन सब का इकोनॉमी पे उतना स्ट्रांग इफेक्ट नहीं आएगा जितना कि 30 ईयर्स एगो आता था, क्योंकि आज आपकी इकोनॉमी आपके आईटी और सेक्टर्स से काफी कुछ मीट होने लगी है, और यह सब इनडायरेक्टली नॉट डायरेक्टली एस्ट्रोफिजिकल स्टडीज का कंट्रीब्यूशन है।
Okay, sir. Thank you, sir. If there is any question in the mind of the participant, can raise their hand. Yes, Nikita.
Sir, is there any availability of any internship programs for astrophysics?
Yes, actually, there is I think you can talk to Professor Shantanu. He knows it very well. Joint astronom एक प्रोग्राम है, ऑल इंडिया लेवल का एग्जाम होता है, उसमें आप अपीयर हों और उसको क्वालिफाई कर लेंगी तो डिफरेंट इंस्टीट्यूशंस सब उसी में से आपको अपने पीएचडी प्रोग्राम के लिए बुलाते हैं, और उसमें अगर आपको उन्होंने सेलेक्ट कर लिया तो फेलोशिप मिलती है, गारंटीड मिलती है। एक तो ये है। दूसरा, आपने देखा होगा इधर इंस्पायर और उस तरह के ढेर सारे प्रोग्राम हैं, तो देयर आर अपॉर्चुनिटीज। वही मैं जैसे कह रहा था, मैं तो इस टॉक में खाली आपको मतलब फैसिलिटीज के बारे में बताया। इस तरह की अपॉर्चुनिटीज हैं, और मैं संक्षेप में इतना ही कह सकता हूं कि साइंस के और ब्रांचेज में भी जो अपॉर्चुनिटीज हैं उससे कम नहीं है, इसमें उसके कंपेटेबल हैं। ये जरूर है कि यू हैव टू वर्क हार्ड, एंड विदाउट दैट नथिंग कैन बी अचीव्ड। हैं अपॉर्चुनिटीज।
Ranjana Jaiswal, you can unmute yourself and ask the question.
Sir, I want to ask that what are the advantage and disadvantage of this dot telescope over the giant meter wave radio telescope?
Oh, it's a very good question. So let me answer. जाइंट मीटर रेडियो टेलीस्कोप, जैसा आपने नाम से ही देखा, वह इलेक्ट्रोमैग्नेटिक रेडिएशन के रेडियो वेवलेंथ को ऑब्जर्व करेगी। तो उसके जो एंटीना होते हैं या जो लाइट कलेक्ट करते हैं वह टोटली डिफरेंट होते हैं, और इसीलिए उसको रेडियो फिजिक्स कहते हैं। जबकि ऑप्टिकल वेवलेंथ के लिए हमारी जैसे आंख है, इट्स आल्सो ए स्मॉल टेलीस्कोप। तो आप डॉट जो है देवस्थल ऑप्टिकल टेलीस्कोप, यह ऑप्टिकल वेवलेंथ जो भी सिलिशियल बॉडी, मान लीजिए आप एक गैलेक्सी ले लीजिए, उस गैलेक्सी से ऑप्टिकल वेवलेंथ पे कितने रेडिएशन कितना इमिट हो रहा है, उसके ऑब्जर्वेशन के लिए डॉट उपयोगी होगी। लेकिन अगर आप रेडियो वेवलेंथ पे ऑब्जर्वेशन को जानना चाहती है कि मीटर वेवलेंथ पर आपके कितना रेडिएशन आ रहा है, तो उसके लिए जीएमआरटी होगी। तो दोनों एक दूसरे के पूरक हैं, दे सप्लीमेंट इंफॉर्मेशन विथ ईच अदर, इनफैक्ट दे आर नॉट कंपीटिंग विथ ईच अदर। और दोनों के लिए जो टेक्नोलॉजी और बाकी सब चीजों के बारे में काफी कुछ अंतर है। हाँ, एक बार जब आप इमेज ले लेते हैं तो इमेज प्रोसेसिंग में काफी कुछ सिमिलरिटी है।
Okay, thank you, sir.
Anyone else have question?
There is a question in chat box. Can you open it?
Sir, there is one more question from Siddharthi. Sir, she is asking that why did India...
How and when will be there universe and
Hello. Sir, there is one more question.
Yeah, how and when will the universe end? Is it that the question?
No, sir, this one is the. Sir, yes, there is one question asked by Mr. Sumit Kumar Tripathi. How and when will universe end?
Yeah. You see, how and when, both are very important question because that's what we study in science. कब, क्यों, कैसे, है ना? तो देखिए, how it will end. Question is, let us take first example of sun. Sun में जैसे हम कहते हैं कि रेडिएशन इतना आ रहा है, तो it cannot be infinite source of energy. तो जब उसके सेंटर में न्यूक्लियर रिएक्शंस जो कि सोर्स ऑफ एनर्जी हैं, वो एग्जॉस्ट होंगे, जिनको हम कहते हैं डेथ ऑफ द स्टार, वो स्टेज आती है और वो तब हम कहते हैं जब सोर्स ऑफ एनर्जी जिस भी कोई गैलेक्सी है या जो भी है, वो जब एग्जॉस्ट कर जाता है, तो दैट्स व्हेन वी विल से इट विल, अच्छा यूनिवर्स इज सच ए अभी तो हम यूनिवर्स को समझ ही नहीं पाए हैं, तो एंड का तो आई मीन स्पेकुलेट करना इट्स एटलीस्ट बियॉन्ड माय कंप्रहेंशन, और मैं I don't think I can answer this question. इतना ही कह सकता हूँ कि हमें इसके बारे में सही जानकारी नहीं है, क्योंकि आगे क्या होगा, कैसे होगा, कैसी चीजें हैं, we don't know, क्योंकि प्रेजेंट यूनिवर्स में ही है कि ये whether it is expanding universe, cyclic universe या क्या है, there are so many debates which are going on. How it will end? Simple answer is, as soon as the source of energy which is keeping these things alive, it exhausts, then that will end. Of course, one problem will be there, that gravitational force will be always there. जैसे आपने अभी देखा होगा ग्रेविटेशनल वेव डिटेक्शन में दो ब्लैक होल्स के मर्जर की वजह से हो रहा है, तो उस तरह की इवेंट्स होंगे, तो ये कॉस्मोलॉजी के लोग थोड़ा बहुत उत्तर दे सकते हैं. आई डोंट थिंक I am capable of answering when it will end.
Sir, there is one more question, and she is asking that why did India recent short satellite launch vehicle fail? Where do we stand in probes which aren't yet fully developed by the other nations?
Right. You see, this failure was because I think ISRO explained it. They are working on it and they are trying to see. It's a sophisticated and complicated things. And once you make any experiment, once you test, then and only then you will know whether it is success or not. So more information, I will be not able to tell you the technical reasons. But ISRO has provided on its website the reasons why it failed and what are they doing. And probe के बारे में जैसा आपने देखा, they are very expensive projects. I mean, खाली सैटेलाइट को लॉन्च करना ही करीब 400 करोड़ रुपया चाहिए, 400 करोड़. So they are very expensive. So क्या होता है कि globally people coordinate. जैसे हमने 3.6 मीटर का भी कहा, तो इसमें क्या है कि ग्लोबल लेवल पे कोलैबोरेशन चल रहा है. So similar things happen here. तो हम एक दूसरे से compete करने के बजाय हम एक दूसरे को मतलब कम्प्लीमेंट करने का प्रयास करते हैं. और उस माने में मैं कहूँगा इंडिया इकोनॉमी की तरह तो हम, इट्स डिफिकल्ट टू क्वांटिफाई, बट वी आर नॉट फार बिहाइंड. आई मीन विद इन 5th 6th नेशन, जैसे चाइना, इंडिया, जापान, जैसे ये 30 मीटर में भी ये सभी कंट्री इन्वॉल्व हैं. तो आई विल से कि हम उस लेवल पे हैं. इकोनॉमी की तरह क्वांटिफाई कर पाना तो बड़ा मुश्किल है.
Thank you, sir. Sir, I don't think anyone has more
I have
questions.
one question. So, am I audible?
Yes.
Yeah.
Okay, sir. So actually, I have seen one number on your slide that for neutron star density was 10 to the power 12 gram per centimeter cube.
Right.
Okay, so can you explain how it's possible that such a small volume contains such a heavy mass?
Oh, you mean neutron star? Why they have such a large density?
Yes, sir.
Sorry?
Yes, sir. 10 to the power
Yeah, yeah.
12.
Yeah, that's right. I can explain you. You see what happened. Neutron star is like a what we call when a star ends its life, depending upon its initial mass, whether if it is less than 1.4 solar mass, it becomes white dwarf. If it is between 1.4 to few solar mass, it becomes neutron star. And if it is more than that, it becomes black hole. So what happened when these, source, nuclear source at the center, it exhausts, the matter, gravity, due to gravity, it falls in and in. And you see, the first what happened, white dwarf means there has to be some pressure. So it's a degeneracy pressure due to electron. आप जानते हैं ना, I mean, the uncertainty principle, I mean, the two particles cannot occupy the same level. तो उस वजह से क्या होता है कि उस प्रेशर से, डिजेनरेसी प्रेशर, जब तक इलेक्ट्रॉन होल्ड करता है तब तक तो व्हाइट ड्वार्फ होता है. बट इवन इफ दैट कोलैप्सेस, इफ द ग्रेविटी फोर्स इज मोर, तो उस केस में नेक्स्ट पार्टिकल जो उसको डिजेनरेसी प्रेशर क्रिएट करके होल्ड कर सकता है वह न्यूट्रॉन है. एंड बाय दैट टाइम डेंसिटी बिकम्स, आई मीन, वेरी लार्ज. कहने का मतलब ये है कि आप ये देख लीजिए कि एक सोलर मास या दो सोलर मास के ऑब्जेक्ट करीब 12 या 14 किलोमीटर डायमीटर के अंतर्गत होते हैं. न्यूट्रॉन स्टार का साइज है. तो आप खाली उससे कैलकुलेट करके देखें तो डेंसिटी बराबर इज इक्वल टू मास डिवाइडेड बाय वॉल्यूम. तो जो मैंने बताया था ना कि सोलर मास को आप देख लीजिए तो 2 × 10⁻³ ग्राम और 12 किलोमीटर का रेडियस लेकर के उसको अगर डिवाइड कर दें तो एवरेज डेंसिटी उसकी बहुत हाई आती है. तो इट इज द फिजिकल कंडीशंस which are responsible for that. I don't know whether you got the answer.
Yeah.
So may I ask one more question?
Please go ahead.
So, as we know, pulsar is a highly rotating neutron star. Then how sound is creating in the pulsar after merging of two neutron star, as we see by LIGO observatory, or even in the black hole there is sound creating after merging the two black hole.
But they are not sound waves. They are gravitational waves.
Okay, we are running out of
So,
time.
Yeah, they are gravitational waves.
I'm extremely sorry.
yes, sir, there is gravitational wave, but I want to ask, there is some sound, then how, from where it is created? Means after colliding of neutron star or black hole, there is some sound creating behind this. Then what is that sound?
No. You see, I think it's a very complex question, and I doubt that sound is originated and it's received by us. It is the gravitational wave which is being generated, and that's what people are trying to detect with LIGO.
Okay, sir, thank you.
आदरपूर्वक नमस्कार. मैं धन्यवाद ज्ञापन के लिए एक ज्ञान धारक के रूप में यहाँ बैठे हैं. इसका कारण हमारे प्रमुख अतिथि